Okay, so we have this concept of the limit as x approaches, for example, a from the left or a from the right. And here's the kind of more formal definition of it. So here's the same notation. Well, we didn't put in the L there, but the L stands for what we think the limit is or what the limit is. So we write this and we say the left-handed limit or the left-hand limit of f as x approaches a from the, where does it say? As x approaches a from the left is equal to L. If we can make the values, so this is kind of the idea that we didn't make it very clear, but here's a little bit more clarity. So we say that something is the limit L if we can make the values of f, remember the values of f when you're thinking about the graph means the height, so if we can make the height of f arbitrarily close to L by taking x to be sufficiently close to a. And also x has to be less than a because we're talking about to the left of a. We have the minus sign there. So what does that say? Going up to here, let's find some examples. So I think this is a better picture here. So let's say this picture here, let's call this function f. And let's talk about where a is equal to 8. So we're going to talk about this point here, or this value of x rather here. So, and we're going to talk about the left-handed limit. So we're going to say as x approaches 8, but from the left, so we put the minus there. So we're only talking about checking values from this side, not from over here, of, and let's call this function f of x, equals, so what is it here? What is the limit? So the limit here, you can see, it's as we choose this value, we get this height. We choose this value, we get this height. We choose this value, we get this height. Choose this value, we get this height. We can see these heights are getting closer and closer to 0. So we would say that probably guess that the limit is 0, or actually it is 0, but according to the picture. So, so what does that 0 mean, or what does it mean that that's the limit, that's the L? So it means that we can get as close to 0. What are we talking about though? We're talking about the function can get as close to 0. And what does the function mean in terms of the picture? It means the height. So it means we can get the height as close to 0 as we want. Isn't that true? If I want to get really close to 0, like only, say, 0.0001 away from 0, I want the distance between the height and 0 to be really tiny, then all I have to do is move sufficiently close to, in this way, move x sufficiently close, and I can be assured that the height will be close to 0. So I just get x sufficiently close to 8, and then the height will be as close as I want to 0. The height will be, or we say the function will be. So that's the idea of the limit, or in this case, the left-handed limit. So that's what they say here. So let's read it again. We say that the left-hand limit of f as x approaches a from the left is equal to L if we can make the values of f of x arbitrarily close to L. So we wanted to make the values of f arbitrarily close to 0. Remember, the picture looks like 8, looks like this, like that. So if we just choose values that are really close to 8 from the left, we can get the height to be really close to what we claim is the limit. In this case, we claim the limit is 0. So if we can make the values of f arbitrarily close to L, or to 0, by taking x to be sufficiently close to a, or sufficiently close to 8. Okay, so that is the idea of limit in a more formal sense. Okay, now with that understanding, maybe we can take another look at this and see why we said the limit doesn't exist. And actually, we said the general limit doesn't exist. By the way, I didn't use that word before, but we said that as x approaches 0, that's what we're talking about at 0. That's where it doesn't exist. We said it does exist, for example, here. But at 0, as x approaches 0, let's call this function, it's signed, but I don't want to write all that, so I'm just going to call it f. So as x approaches 0, this function, we said the limit did not exist. But by the way, this is called the general limit when we don't have a plus here and we don't have a minus up here. That's called the general limit. So we said that the general limit doesn't exist, but actually not only does the general limit not exist, but for example, this also does not exist. So what does this mean? If we only look at values coming in from the right, even that doesn't exist. Now, how can we see that here with that new understanding of what we mean by limit? So if we said, oh, I think it's equal to, let's say, 0.5. I think the limit is equal to 0.5. So I think it's 0.5. So that means that we can get as close as we want to 0.5 if we choose x to be close enough. I shouldn't use this color. I use green. If we choose x to be close enough to 0, then we can assure that we are very close, always very close to 0.5. But that's not possible. No matter how close I get to 0, this thing's going to jump up and down and not stay super close to 0.5. Now, admittedly, this is not, the way I've stated that is not exactly clear. But anyway, I'm going to say it that way. So as we get, no matter how close we get to 0, this thing is going to always be jumping up and down. And we can't say, oh, I need it to be this close, always. Can you get it always to be this close by getting close enough to 0? No. No matter how close you get to 0, it's always going to jump out of this range here. And so I can't make it within this range, no matter how close I get to 0. That's the kind of idea here. Okay, we didn't state it completely precisely, or we didn't show it exactly precisely, but that's the idea. Okay, so let's look at this picture, and let's do a little practice here, practice our understanding of limits. So let's ask what happens as x approaches 2 from the left. What happens when x approaches 2 from the right? What happens when x approaches 5 from the left, 5 from the right, and so on. Okay, so this function is called g, so I'll write g here. So let's talk about as x approaches 2 from the left. So that's coming in here, 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 here. And we want to know about the height. Remember, the function means the height in terms of the picture. We want to know about the height of the function. So it's, it's over here, it's like here, this high, then it's this high, then you can see that it's approaching 3. So we can say 3. The height is approaching 3 as x comes in to 2 from the left-hand side. However, when x comes into 2 from the right-hand side, you would never guess 3 if I told you, oh, the height is here, the height is here, the height is here, the height is here. You're going to guess what? You're going to guess 1. So the limit for this one is 1. So these are not the same. As you come in from this side, you'd guess 3. As you come in from this side, whoops, not 1. Yeah, you'd guess 1. So they're not the same. So we didn't say this that clearly yet, I don't think, but if the left-handed limit is not equal to the right-handed limit, which it's not here, the left-handed limit is 3, and the right-handed limit is 1. In that case, we say that general limit does not exist, because it has to be a single number, and it's not. If you come in from this side, you get one number. If you come in from this side, it's a different number, so it's not a single number for the general limit. So we would say D and E. Let's just practice one other thing here. What is f exactly at? So coming in from the left of 2 to the right of 2. What is f of 2 exactly? Well, they both have open circles, so actually it's not defined. Actually, I guess we write dne again, but that's a different dne. I guess we should say not defined. I guess it's the same thing, actually. I mean, it's the same words. Not defined does not exist, but it has a it's a different meaning here. Anyway, at 2, it's not defined. Okay, so let's just clarify that. Okay, make sure we agree about that. Okay, now let's look at 5. So we want to look at 5. We want to look at 5. We want to look at 5. But before we do that, let's ask, what is f of 5? What's the height of the function at 5? So here's 5, and here's the function. But you can see this dot means the height is not up here. It means down here. I think that's supposed to be 1. Maybe it's not. I think it's supposed to be 1. So let's think that it's 1. So the height is 1. F of 5 is equal to 1. But that's only, that's one question. But these are different questions. So what about as x gets close to 5, but from the left? So you're asking about the height, and it seems to be, I guess this is 2, and I guess it's 2. So the answer is 2. How about as we get close to 5, but from the right, then it's also 2. It's also approaching the same thing. So this is equal to also 2. So in this case, so in the previous case, the left-handed limit was 3 and the right-handed limit was 1, so they weren't equal. So this was dne, doesn't exist, because both have to be equal for this to exist. But here, they are both equal. So this exists and is equal to 2. Okay, that's the idea. If the left equals the right, then the general, this is called the general one, is what they are both equal to, which is 2. Okay. All right. So we have this is a nice example of limit questions using a graphical understanding. So just to let you know, a little bit later, we're going to talk about continuous. A function is continuous, and we're going to say that like this function is not continuous here at a, which seems to make sense, right? It's not continuous, it jumps, right? So we're going to talk about this function as being not continuous at a, or we'd say here, this function is not continuous at 5. And we're going to use as the definition just what we got here, or part of what we got here. That is, that the left-handed limit equals the right-handed limit, and that is that the limit is equal to something, but even though the limit is equal to something, the actual value is different. So the limit is up here at 2, but the actual height of the function here at 5 is not 2, it's 1. So that's how we identify the fact that it's not continuous. Of course, just looking at it, it doesn't look continuous, but we want to write a kind of mathematical definition of what we mean by continuous. So we're going to use this kind of approach. But anyway, we'll do that later. Just wanted to bring that up right now. Okay, now let's do a slightly different concept of limit, or use limits in a slightly different way. So we've been writing limits like the limit as x. I think the last one we did was, what was it? 5. We did that one. I think it was g of x we called it. And we had some answer here. And I think we also looked at another previous example was like as x approaches 8. We did that kind of limit, and so on. But we're going to do a different kind of limit now. And that is, we're going to allow ourselves to kind of extend this idea of limit so that we're going to write something like this. The limit as x approaches not 5, not 8, not 1, not 2, but infinity. Now that's kind of using it differently than here, because this is a number, and this is not really a number. So what do we mean even by writing this? What we're asking is, suppose we have a function that looks like this, if you know what I mean by that. So what am I trying to draw there? I'm trying to say that as we move to the right, it's going down, 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 but I'm trying to show, I don't know if I can draw it anywhere near nicely, but I'm trying to show that it actually never touches the x-axis, but it gets as close to the x-axis as we want if we go out far enough. That's what I'm trying to show in this picture. So this would be asking, what happens sort of if you keep moving to the right? That's what this means. If you kept moving to the right, is there anything you can state about this picture? Well, yeah, I just said I'm trying to show what? That as you move out to the right, it gets closer and closer to the x-axis, but never touches. So what does that mean? Well, when I said it gets closer and closer, what am I talking about? I'm talking about the height, or we say the function. So suppose this function is f. If I say what happens to f, I'm talking about what happens to the height. And we just said that what I mean by that is, what I'm trying to draw there is that it gets closer and closer to the height, gets closer and closer to 0, because I'm saying it gets closer and closer to the x-axis. That means its height is getting closer and closer to 0. So we're going to allow ourselves to ask this. What happens as x gets bigger and bigger? So it's kind of different than this, right? Because as I said, this is a number. This is something else. Okay, so here, this picture, we were asked to sort of get used to this kind of function. So what does it look like? Well, you can see, okay, let's see, what does it look like? It's 1 over x squared. So suppose I put in x equals 1. So let's say here's 1. So suppose I put that in, I get 1 over 1 squared. So apparently the height is 1. I shouldn't be using this color, but I am now, so I'll just stick with it. 1, 1. And how about if I put in 2? Then what do I get? I get 1 over 2 squared, which is 1/4. So it's getting smaller. And what if I put in a big number for x, like say 100? So I go way out. What happens? I get 1 over 100 squared, which is 1 over 10,000, which is very small, or in other words, very close to 0. So this looks somewhat like this does, at least on the right-hand side. Now on the other side, it looks like this. So whatever. Okay? So if I ask what's happening to this as x goes to infinity, it's the same thing as here. What's happening? If I ask what's happening to f as x goes to infinity, I'm asking about the height of this graph, and the answer is 0 again, just like it was here. So that's the kind of thing we can ask, and in this case we can answer it. So the limit as x goes to infinity of this function here, I'll call it f, is 0, according to the way they've drawn the picture. Okay, and then of course we could also write this, the limit as x goes to minus infinity. And so what does that mean? What is that asking? It's saying when we move in this direction, is there something we can say? And yeah, it also happens to be 0. Okay, let's try another picture. Let's suppose we have this picture. So suppose this is 5, and it looks like this. So what I'm trying to say, obviously, is getting closer and closer to a height of 5. I can't draw that very well. So let's call this function g. So if we ask this question, so you can either write g or g of x, either way, it's okay. So what's the answer? According to what I'm trying to draw, the answer is 5. Okay, so we would say that. Now there's nothing over here, so we don't talk about going to the left. I didn't draw any picture there. Okay, now let's take a different function. Suppose we had a function like parabola. So maybe this is f of x equals x squared. And if I said, let's just go back and practice one thing before I go on to this, continue with this topic. Suppose we say 3. What is the height at 3? F of 3, of course, is 9, right? And then, of course, we can say the coordinates of this point are 3, 9. Okay, but if we ask, what's the limit as x approaches 3 of this function, f of x squared, what's the answer? So, if we come in from the left, we're going to guess, we're going to guess 9. And if we come in from the right, we're going to guess 9 also. So the answer is 9. So it's the same as the value there. Okay, so that's easy actually. Okay, but now we want to ask a different question. That was just kind of just an extra, I just want to make that point. But now we want to ask a different question, and that is this. So what would you say? So as you move in this direction with this, obviously it's just getting bigger and bigger. So you would say, is there a number that it's approaching? No, there's no number, right? Okay, well, you wouldn't say, oh, it's approaching 100, because obviously after a little while it goes way past 100. It never gets close to 100 again. So it's not approaching 100, it's not approaching 1,000, it's approaching 10,000, 100,000, a million, or whatever. There's no number that it's approaching, it's just getting bigger and bigger. So remember, if there's no number, we should say D and E, but actually we don't say that. And I don't really like what they do here, because this is the right answer, it doesn't exist. But they kind of cheat. And they say, okay, well, we agree that it doesn't exist, but we're going to write this. So why? Okay, so first of all, this is not a number, so we're not really lying, because we said there's no number, and this is not a number, so okay, so we didn't cheat. And this provides a little bit more information than just writing D and E. Okay, we could write D and E. I think that would be okay to write D and E. But they choose to put this there instead to say, okay, it's D and E, but this also tells me that it's not just D and E like this. For example, we said that if you have something like this and something like that, and then you ask at A, and the answer is the general limit does not exist. It's not just like that. We're going to say, we're going to provide a little bit more information, and that is that this just means that it gets bigger and bigger. Okay, so we'll write that this limit is, instead of D and E, they write infinity, or positive infinity. Okay? And then we can also ask here, we can also do this, the limit of the same function as x approaches minus infinity. So that means as we go in that direction, then what happens? Also, there's no number, and we could write D and E, but they want us to write, again, infinity. Okay, now suppose we have a different function, f of x equals x cubed. So if you remember, that is going to look like this, but then it's going to come and do that. It's not going to go back up. So for this function, we could say the limit of this function as x goes to infinity is infinity, or positive infinity, if you guess it's good enough. That's okay. But what about this? The limit as x goes to minus infinity, that if we move in this direction, what would we say? Would we say it goes to infinity? No, we would say it goes to minus infinity. Okay, so we can write these statements for this kind of picture here. Okay? Okay, let's take another example. So let's take this example, and we have an interesting picture here, and it's called that. It's called f again. Always use f. So this is an interesting picture. So we could say, okay, when x equals this, of course the height is here. When x equals this, of course the height is here. When x equals this, of course the height is here. When x equals this, the height is 0, and so on. But this picture does something strange at a. So let's talk about what it does at a. So let's talk about the limit of this function as x, and let's be a little bit easier about it. So let's just say a from the right. So what happens? What happens to the height? Well, you can see that what they're trying to say is it's going down. Going to, what do they mean? They mean it's going to minus infinity. So we're going to write minus infinity there. Okay? And then what if we do it from the left? Well, I think the same thing. So now what's happening as we move in from the left, the same thing actually. I mean, they could have drawn it to go up here, but they didn't, drawing it to go down here. So it's also equal to minus infinity. Okay? And what else can we do here? Well, we don't really exactly know what they mean by this. We just covered this part and this part. Oh, by the way, we can also say this, I guess. Limit as x goes to a, without a left or a right here, without a plus or minus there, we can actually, they allow us to write this. Okay? So if these two are equal, we're allowed to write this one as whatever they're equal to. So this is minus infinity and minus infinity, so we can write the general limit is also minus infinity. Okay, now what about here? In this one, I guess they mean that it's going up forever, and I guess they mean this one is going down forever. So if that's what they mean, then we could write the limit of f as x goes to infinity, positive infinity, is, I guess we could say infinity or positive infinity, and we could write the limit, so that's this behavior here, and then we could write the limit of f as x goes to minus infinity, so that's here, this direction, so I guess they're saying it goes down, so it's minus infinity, I guess. Okay, so that's this example.